All right, this is our last section in Chapter 8 that we're going to talk about today. And it is static equilibrium. Okay, so static, that term, when we think of something that's static, we tend to think of it being still or not moving. And equilibrium, again, means it's equal, it's staying still. So something that is in static equilibrium is an object that is at rest. Is an object at rest and that remains at rest. And that means there are two conditions that have to be followed. The total force acting on the object has to be zero, so that means that there's no linear acceleration. And the total torque acting on the object must be zero, so there's no angular acceleration. So something that's in static equilibrium is not moving. It's at rest and it stays at rest. It's not moving linearly, and it is not moving rotationally. Okay, so that is what we're talking about with static equilibrium. I forgot to clear my screen. I bet it won't. There it goes. All right, so an application or where we would use this or when this happens would be, let's say you're trying to support this child that's sitting on this plank by holding the plank at either end. So we're talking about anything that's being held at either end and then has a weight in the middle. So in order for that to stay still and for that child to not go flying in one direction or the other, for the plank to not go rotating one direction or the other, you have to have static equilibrium. So that means that the forces acting on the plank and the force of gravity on the child, all of those things have to be zero. So there's actually three forces acting on this plank. The F1 for the lady, the F2 for the man, and then the force of the child acting downward. So our total forces in this situation are F1 plus F2 minus mg, and all three of those forces have to be zero. Otherwise, this plank is going to rotate, and our little kid's going to go flying off. So to make sure that we are in static equilibrium, and to see how much force we would have to put in to be in static equilibrium, we need to choose one of those forces, not one end, but we choose one force to be our axis of rotation. So if the kid wasn't sitting on it, pick a force, pick an end, which end would be our axis of rotation. You can pick either end you want. You want to pick an end that's going to make the math simplest, because remember, when you're at the axis of rotation, that means that force that's exerted there has zero torque. Okay, so the force exerted at the axis of rotation, it has zero torque. So you want to pick one of those forces to be your axis of rotation. Which one? It doesn't really matter. Okay, so that means the other force is going to produce a torque of whatever F2 is times the length of the plank times its radius, or how far it is from the axis of rotation. And if you could rotate this, it would rotate counterclockwise. So you're looking at the man. If F1, the woman, is our axis of rotation, we don't have the child sitting on it, you apply a force upward at F2, that means that plank is going to move or rotate counterclockwise. So that's our F2, and that torque would be equal to the force that's applied at F2 times the length of that plank. And then, of course, we have the child's weight, is mg, mass times gravity. And so that torque would be equal to mass times gravity times 3/4 the length of the plank, because the kid is sitting 3/4 of the way between the axis of rotation, between one end and the other end. He's sitting not quite in the middle, but also not on one end. And if you think about his force acting downward, so if you could rotate from his point, he would rotate clockwise. Okay. All right, so those are all of our forces. So let's clear this and let's go back and look at our diagram again. Okay, so here's our axis of rotation right here. So F2 is applied at the other end of the plank. Okay, so the length from the axis of rotation would be L. So the torque is going to be F2 times L. The kid is just sitting 3/4 of the way from the axis of rotation. So he's going mg times 3/4 the length of the plank. And if you notice, he's being subtracted there because that force is acting downward. It's acting clockwise, whereas the other one is acting counterclockwise. Woo, goodness. Okay. So here's the math for all of that. So F1, since it's at the axis of rotation, does not produce any torque, so that's going to be 0. Plus F2 times L plus mg times 3/4 L. And all three of those have to add up, or negative mg times 3/4 L. And all three of those have to add up to 0. So if we just do the algebra and solve for F2, we get F2 is equal to mg, 3/4 mg. And then we plug that back into our original equation. So you remember our original equation was F1 plus F2 minus mg equals 0. We take and plug this back in up here and solve for F1, and that gives us 1/4 mg. Okay. So it doesn't matter, like I said, it does not matter which end you choose as the axis of rotation. We choose that arbitrarily. And you can choose either one you want, whichever is one most convenient. And later on, it's going to be whichever one gives you the easiest math. Okay. All right. Oops. All right, so center of mass. Center of mass is the point at which an object can be balanced. And so most of the time, the object behaves as if all of its mass is concentrated in the literal center of the object. But that's not always, or that's not necessarily true. The location of the center of mass can be calculated. And one way that we calculate that is using this formula that you see here. So the center of mass of an object can be calculated by taking the first mass times the distance from the axis of rotation, plus the second mass times the distance from the axis of rotation, divided by the total masses. So here's an example of what we're talking about. We have two masses, a large and a small. So you can see in this first example that the center of mass is actually going to be closer to the larger object. If there is a larger object, center of mass is closer to the larger mass, and it's equidistant between equal masses. So if you have two of the same size mass, that's going to give you the center of mass between those two things is going to be literally in the center. If you have two different size objects, the center of mass is going to be closest to the bigger mass, whichever that is. Okay. An object can always be, when an object is supported at its center of mass, there is static equilibrium. So because all the torques are balanced, so it's not going to be rotating. It will literally be still, hang still. Think about a plumb line that carpenters use. And that's why they use it, because it's going to give them that straight line. So that plumb, that weight at the end, when you suspend it, and it's all of its center of mass is right there, suspended, then it's not going to rotate or swing back and forth. So that's how you know that it's plumb or that it's straight, because it just hangs straight down. It doesn't rotate. It doesn't swing back and forth or anything like that. Okay. So with that said, then we can find the center of mass also by looking at the suspension point. So if we can suspend an object and have it not move or have it not rotate, so the torque due to gravity is zero, when the center of mass of an object is directly below the suspension point. So if we hang something and it's not rotating, it's not moving, then we know that torque is zero because you're right at it's just due to gravity, and gravity is acting right there on the axis of rotation, which means its torque is zero. And so its center of mass is right below the suspension point. So that's another way that we can find the center of mass. Okay, so if you allow an object with any shape to hang freely, its center of mass will be directly below its suspension point. Now, it means hang freely. It can't be swinging back and forth or moving around or rotating. It's got to just be hanging. Wherever it's hanging and just being still, right below that point is its center of mass. So the center mass of an irregular shaped object, such as a piece of wood cut in the United States. So you see that shape. That's an irregular shape. It's not like a pendulum bob or a plumb bob. It's not a sphere. It's not a drop. It's a weird shape. We can locate its center of mass when we suspend it from two or more points. The center of mass is going to be in the intersection of the vertical lines extending downward from that suspension point. So if we suspend it from points A and B, where those lines for A and B cross, that's its center of mass. So if we hung it here and hung it here, and we drew straight lines from those points, where those two lines cross, that is where the center of mass is. And I believe, yes, that is it for static equilibrium. So we will be working our practice problems in class. So if you have any questions, make sure you bring them to class and we'll go over them.